Hello, Verma sir, are you there? Hello. Good afternoon, everyone. Now session is started for hands-on session. So I invite Narendra Kumar sir and Professor Mohanlal Verma sir for hand-on session. Sir, your speaker is off. Like you are not audible.
चालू करो. हाँ नरेंद्र.
Yes, sir.
So I think give just an overview whatever we have performed yesterday first 10 minutes.
Okay.
Then today what we have to do, we have to optimize the system. So
Yes, then we will.
DAS, PDAS and DAN. Can we?
Yes, yes, sir.
So
So welcome back all the participants. Yes, yes, sir.
For some more time or it's okay, we should start.
Narendra Kumar sir.
Yes, just give me 1 minute. I'm trying to connect from my computer. Ma'am, can you allow me to share my screen?
Yes, your host, you can share.
Ma'am, can you make my lab computer? The name is Narendra Kumar, the second one. Make it as a host.
Sir, both is in co-host.
Okay. Yeah, now I can.
Kumar, Narendra and Narendra Kumar, both is.
Yes. So I welcome all the participants in day 2 hands-on session. yesterday we did some basic siesta calculation. We also generated the FDF file using GDIS. So today we will do the full optimization or relaxation. Then we will plot band density of state and projected density of state. I already shared the Day-2 tutorial with you. Kindly download it. Take 2 to 3 minutes and download it, and let me know when you download the Day-2 tutorial. Okay. Sajal Vishwas sir get. Okay.
Narendra, wait for just a few minutes. Here in the lab, students are just lagging behind.
Okay, sir, no problem.
Okay,
I shared the link,
2 or
sir.
3 minutes. Yeah, you have shared and they are not ready. Okay, just 2 minutes.
Okay, sir. Kindly let me know when to start. So yesterday we did basic size calculation with single zeta, double zeta, single zeta polarization, then double zeta. How many of you did that calculation at your home? If you have anyone have any question, you can ask.
Hello, sir. Am I audible, sir?
Yes, but your voice is too low.
Now, sir. Hello, sir. It is okay, sir.
Yes, yes, please.
Sir, I have calculated using many options. In some
Yes,
cases, the lattice constant values are showing same result. Okay, sir.
yes. I think in that case, you didn't copy that relaxed file I said you in the morning.
Yes, sir. Yes, sir.
Just copy the relaxed file that we did yesterday in T1 folder
Yes, sir. Yes, sir.
and try with that one.
Okay, sir. Okay.
Yes, Naren, proceed. Is there an issue?
No, I'm waiting for you.
Okay, okay.
So yesterday we did that basis size calculation. Then we created the FDF file using GDIS. Today we will do the band and toss calculation. So I shared that Day-2 folder. I hope everyone get it. So if you open this folder and go to this T2 directory, you can see here. Yesterday we did the example of silicon bulk system. Today we will do the graphene system, that is 2D sheet. If you right click, then open terminal here. ls. So we have a FDF file here that is .c.fdf file. Let's visualize it using GDIS software. So what we will do GDIS, then our input file name, that is carbon.fdf, and enter. You can see this is just 2-atom FDF file. If I go to this image here in the left corner, click here, then go to image and repeat it along X and Y. And make supercell. Now you can see this is your graphene nanosheet. And if you repeat in G direction or Z direction, you can see there is a vacuum, the space between this layer, the first layer and the second layer. That means our system is periodic only in 2 directions, X and Y. This is graphene sheet. But when we do the optimization, we usually deal with a unit cell, or we can say the small number of atoms we usually do when we do the optimization, because this is just a periodic image of that 2 atom. This big sheet here in this side is just a periodic image of this one. So if we optimize or relax these 2 atoms, we can get a relaxed structure of graphene sheet. And then you can enlarge it, and if you want to do some doping, so okay, just cross it now. Now, to optimize any system, we have to follow 4 main steps in Siesta. Number 1 is cutoff, that is mesh cutoff optimization. Then the kpoint optimization and lattice optimization. And by taking the optimized value of these 1, 2, 3 steps, we will do the final optimization. So here, what we will do today, first we will optimize this mesh cutoff energy. Then we will optimize this k points. Then third step, I said here, this lattice constant, this one. Then by taking all these optimized value, we will do the final optimization. Okay, so now how you can optimize your mesh cutoff energy? Suppose so how we will optimize this mesh cutoff energy? You have to change this value and check the So what you have to do, you have to change this value and calculate the energy according to that value. Suppose how I can do, let's change it to first 50 and then run the siesta. Then I will change it to 100, then run the siesta, then 150 and so on. One option is you can do it manually. The another option, you can write a script that can automatically change your value here and calculate total energy. So for that, Verma sir already created a script named energy cutoff. If you go to this folder cutoff, here you can see you have script cutoff.sh. Just double click it and open it. The first thing you have to do, you have to copy your FDF file, the complete FDF file, that is carbon.fdf. Just copy all the parameter, copy it and paste it inside that script. Here you can see cat c.fdf, then EOF just below that, and above that COF space, and paste your FDF file. How many of you did this step? So, okay. So what this script will do for you, it is changing your cutoff from 50 to 500, and then calculate a siesta and calculate total energy. So what this script will be do for you, let me show you here. This script, here you have mass cutoff. This script will change your mass cutoff value first 50 readable, and then run the siesta and calculate energy. The next step, it will change your readable with step 50. That means your next mass cutoff would be 100 readable. Then run the siesta and calculate the energy according to this 100 Rydberg, and so on up to 500 Rydberg. Run the siesta and calculate the energy for you. So just set this parameter 50. In this step of 50 up to 500, you can increase it to 600 or 400, whatever you want. Then make sure here your mesh cut off, it was 350 initial. Now I am changing this parameter with $I. So it is just a variable. This script will read this $I and change it with 50 and run the siesta. In the next step, this script will change this $I with 100 and so on. Just save it. Make sure your mesh cutoff is $I Rydberg. $I means I set the variable, and this variable is varying from 50 to 500. And save it. Now open a terminal, right click and open a terminal. So you have to do ls first. Now you have hidden files is showing here. Let me remove it. Or just you can see you have this script cutoff.sh. So first thing you have to press chmod. This is change mode plus x and script cutoff.sh. If you hit again ls, you can see the mode of your script is changed now. You can see it in green color. Before running this script, make sure in the end of this script here, if you install siesta binary as a siesta, then you have to write siesta. If your siesta binary is siesta.exe, then it should be siesta.exe. But here in our case, we have only siesta. The siesta binary file is siesta. Okay, let me save it, just close. How you will be run this script? You have to press / and script cutoff.sh. What I did, / then I write s and press tab 2 times and then hit enter. It will start running a siesta calculation. If you see in the background, you can see a folder with 50 is created here and it is running. One thing to make sure here, I'm just stopping this calculation. I did one mistake here. When you have to do this calculation, this optimization of your cutoff and k points and lattice as well, you have to keep your CG step 0. See, just 2 line behind this mesh cutoff, you can see the CG steps are 1000. So what I said, I need 0 CG step here. Everyone, please make sure your CG step should be 0 to run this script, let me save it and cross it. I'm restarting the calculation. It is running. See, 50, 100, 150, 200, 250. What this script is doing, creating a folder name 50 with this type of 50 and so on up to 500. Then in each folder it is replacing our mass cutoff value with same parameter like 50 read work here and calculate the energy, total energy of system. Similarly for 100, our mass cutoff is 100 and running the siesta and calculate the energy and so on up to 500. The calculation is finished. So now we have 50 to 500 mesh cutoff and each mesh cutoff correspond to a particular energy. So we need to check that energy and we will check how the energy is changing with different mesh cutoff. So this mesh cutoff is very important in the term of accuracy and computational cost. So now what will we do? We will grab that energy using the grep command that we learned yesterday. The command was grep space semicolons the energy. Okay, if you open any directory, you can see each directory has one out file here, carbon.out. If you open this file, press Ctrl F and search for total. Total means total energy. You can get, here is our total energy. So we will use this keyword in grep command to copy energy from each folder. What will we do? Grep colon and total D capital and OTAL small space equal to R slash R dot out and save this energy in, let's say, energy dot dat. Hit enter. You can see here a file energy dot dat is created. If you open this file, you can see it is saying 50/c dot out colon siesta total, and the energy is this. Okay, so what you have to do next command is gedit energy dot dat and hit enter. Now we don't want these lines. We just want the data in the term of X and Y column, like the lattice, not lattice, the mesh cutoff and the corresponding energy. We don't want these extra text is here. So to remove this, just press Ctrl H, copy this text from here and paste here and replace it with nothing and replace all. Close. Now the first line is our mesh cutoff, and the second is energy. And save it. Pause it. So plot this energy. We have to use XM grace. So how we will do XM grace space energy dot dat. A kind of box is appear in front of you. So now just double click on this line, and here you can see the symbol properties, and type of symbol is none. You can choose it circle and then go to the symbols. Then the symbol fill with color this. You can change the color as well if you want red or magenta or blue, and then the pattern is this one, and press accept. So here this is the trend of the energy that is changing with mesh cutoff. When the mesh cutoff in this line, in this side, this one is mesh cut off in readwork, and along Y side it is energy in electron volt. So when the mesh cutoff 50, the energy is very high. Then when the mesh cutoff 100, you can see the sudden change in the energy. And as you increase the mesh cutoff, the energy is converging, or you can say going toward the minima. So here you can see around 350. After this 350 read work, the energy is almost stable, or you can go up to 700 to check it. But for now, we can say after 300, 350 or 400, our energy is just stable. So that from here we can say our mass cutoff energy is 350 read work. So save it. How you will we save this file? Go to file, press save as, and then give the name. Let's say this is energy versus mass cutoff of .agr. This is XMGrace, and the extension of this file is agr. Like in the text file, the extension of the file is txt. In the PDF file, the extension is PDF. In XMGrace, the extension is .agr. That's okay. If you want to print it, you can go to print setup, and you can choose it as a EPS, JPG, PNG format. I'm going with JPG. Press OK, apply. Then again, before that, I was here in the print setup. Now print and cross it. Now you can see your energy cutoff .jpg file is here. How many of you did this step? Up to now, anyone has any? Someone is asking to repeat the process. Okay, I'm repeating. Let me delete it. So what I did, this one is our input file that is for graphene. And here to optimize the structure, we have 4 main steps. First one is the mesh cutoff energy optimization. The second one is the kpoint optimization. Third one is lattice optimization. And then the final optimization. So first one is the mesh cutoff. I open this file. Here I have script.sh. Just open it, double click it. Here, this is the script written by Dr. Mohan L. Verma sir. So this script, in this script, you have to copy your FDF file first. Just all the parameter in your FDF file, just copy, and inside your script, just paste it below this EOF and above this EOF, the last EOF. I'm deleting everything between these and paste my FD file. Now, I said the first step is mesh cutoff optimization. Here is our mesh cutoff parameter. So we need to vary it to check the total energy corresponding to different mesh cutoff. So how we will be do this? We will vary this parameter. Either you can do it manually, or you can do it using a script. So I'm using here with script to make my life easy. So what I will do, I will make this script is created by Verma sir. So what he did, he created a parameter $I to vary this value according to the sequence he gave here. So what this script will be do for you, this script here, you have to define the sequence. Here you define sequence, let's say 50, 50, 500. What does it mean? It means it will change the value of match cutoff with starting from 50 with this step of 50 up to 500. Or you can do one thing, you can start it from 100 within the step of 20, let's say up to 500, or within this step of 50 up to 700. So now I define the sequence here. Let's say 100 within the step of 50 to 700, and this script will calculate energy corresponding to each mesh cutoff. What we are trying to do here, changing the mesh cutoff and calculate the value, energy value corresponding to that mesh cutoff. Changing the mesh cutoff and calculate the energy corresponding to that mesh cutoff. Like in 50 read work, what will be the energy? In 100 read work, what will be the energy? 150 read work, what will be the energy? And so on up to 500. So now, when you define the sequence, your next step is to make sure your CG step is 0 and make this value as a variable parameter $I. $I means when this script will be run, it will check where is the $I, and this script will replace this $I with 100 and run the siesta for you. Then it will go for next step. It is kind of do loop. It will go for next value, that is 100. You did 100. First step you did 100, then it will add plus your next value is 150. Then it will run the siesta and add the 50 in this. Then your next mesh cutoff value is 200 and so on. So let me run it. I just save it. Pause. Was here. Open terminal here. First command I gave chmod plus x and then script name, that is script cutoff.sh. and hit enter. Press ls. You can see the mode is changed. Then you have to press dot slash and script underscore cutoff dot sh. Enter. It will start running from 100 now. Then 150. If you open this 100 folder, here you can see your FDF file where it is. FDF file. Check the mesh cutoff. The mesh cutoff is 100 here, and it run the siesta, and in your output file, it will give you a energy corresponding to 100 readwork mesh cutoff. In 150, if you open your FDF file, you can see your mesh cutoff is 150 and it is running siesta. Then your 200, check your FDF file, your mesh cutoff energy is 200 readwork, and so on. It is running. Okay, I am crossing it now. Okay, so this script is each folder has out file. Like yesterday we did a siesta calculation, then we have one out file, and that out file has a less coordinate. In that case, in this case, we have a out file. In that file we have total energy. If we open this out file and search for total is equal to total, you can get a total energy is minus 323.404872 electron volt. Now you have to graph this all energy and check the energy versus readwork graph. Mesh cutoff, you can say. We want to plot energy versus readwork to check the behavior of how energy is changing as we increase the mesh cutoff. So for that, first let's copy all the energies inside all these folder. So for that, how we will copy this energy? We will do grep command, grep space is colon and press total space equal to and star slash star dot out and save this file using this, or you can do like this, less than column and energy dot that. Enter. If you hit ls, now you can see energy dot that file is created here. Inside this energy dot that file, all the energies inside these directories you have in this data file here. So you can open this file using gedit energy.dat. Here you can see you have all the energy correspond to 100, 150, 200, 250, and so on. So what I want now, I want plot this value, this read work. Here I said read work. It should be like in 100, 150, 200, and 250, and so on. So here, first I need to remove this unwanted text. What I will be doing, I press Control H to find and replace Control and H, and copy this text from here to here, copy and paste it here, and replace it with nothing and replace all. Now you can see your data in X and Y format. Just save it, cross it, and plot it in XM grace. XM grace, then your file name, that is energy.dat, and hit enter. See your energy is, how your energy is changing. Because I cross this calculation, then there might be any issue, but you can see here, yeah, this one I crossed, the last one, it is up to 550. See, the energy is changing. It is minimize. It is going to down as we increase our. Let me open that, the old one. XM Grace start.agr. So here you can see the energy is changing as we increase the mesh cutoff energy. Here the energy is stable. You can say stable. Either it might be go down as you will go to higher value, but you can see after 450, 350 or 400, it is almost stable. So our mesh cutoff, you can say, is 350 read work. So in further calculation, we will use our mesh cutoff as 350. Our mesh cutoff is 350 read work. We will use this value now because we plot energy versus cutoff graph, and you can see after a particular value, that is 350, the energy is almost stable. So now go to kpoint, open this script the kpoint script, and same copy this your FDF file, copy it and paste it here just below that EOF and above this EOF, paste it here. Now we did the mesh cutoff optimization and we found our mesh cutoff is 350, or you can say the 400. Higher the mesh cutoff, higher the accuracy. Around between 350 and 400, it is stable. So the next step is kpoint optimization. We optimize mesh cutoff. Now we will move to kpoint. Now here, because this is our 2D system, so we will vary the parameter only x and y, because our graphing sheet is only periodic in x and y direction, not in z direction. So in this k grid block, you can see it was 12, 12, 1. We will vary and check the energy. How we will vary? We have to put $I icon here. Similarly, in y direction and z direction, we will keep it 1, because it is not periodic in z direction or z direction. Again, make sure your CG steps, MD numerical NUM CG steps are 0, and you have to put the relaxed mesh cutoff that you optimize just in step number 1 here. Save it and cross everything. Let me recheck it again. We put the mesh cutoff energy that we optimize in step number 1. Then we put the dollar icon in the kpoint block, x and y direction, and our CG steps are 0. Here you have to give the value, your kpoint value. You can increase it like 3 within this step of 2 to, let's say, 25. Save it, pause it, open a terminal. Again, you have to give the same command, that is chmod space plus x, and your file name is, that is script underscore kpoint.sh. I just write s and press tab. It will appear, and hit enter. Now you can type ls. You can see your script is in green color now. That means in the binary form. You can run it using /script.sh. This script will do the same thing for us. We have k points. We will vary our k point 2 cross 2 cross 1. Then in this step of 2, then next one is 5 cross 5 cross 1. then 7 cross 7 cross 1, 9 cross 9 cross 1, and so on up to 25 cross 25 cross 1. So here you can see I'm using 2 cross 2 cross 1. Why? Because that graphene sheet is periodic only in X and Y direction. Suppose you have 3D direction like silicon that we did yesterday, that is a bulk system. So that one is bulk means periodic in X, Y, and G. In the case of silicon, in that case, we have to vary this parameter as well. If we have silicon, or we can not silicon, but we can say the bulk system. If we have 1D system, then 1D means like carbon nanotube. So what we will be do then in that case, our K point might be in like 2 cross 1 cross 1, then 3 cross 1 cross 1, and so on up to whatever you want. Let's say 25 cross 1 cross 1. Here you can see as the periodicity is here periodicity is 2D. That's why 7 7 cross 1, 9 9 1, 20, 5 cross 5 cross 1. If the periodicity is only in one direction, in that case we have 2 cross 1, means periodicity of our structure is only in one direction, only in X direction, X, Y, and G. If we have 3D system, for 3D, that is like 2 cross 2 cross 2, 3 cross 3 cross 3. We are varying X, Y, and G, all the parameters. Okay, done. Our calculation is finished. So what we will do here, we are changing our parameter from 3 to 25. That means we are changing our K point from 3 to 25 and calculate the total energy correspond to each K points. Like in what will be the energy in the case of 221, what will be the energy in the case of 331, and what will be the energy in 4455, and so on. Now again the same step will follow. We are going to grab that energy, grab space, columns, semicolons, and total space equal to star dot out, and save this file as a energy dot dat and hit enter. That is ENE energy dot dat. Now open this file just to check it. What is inside this? Gedit energy dot dat. Here the same you can see in the case of 3, 5, 7, we have energy something. In the case of 331, we have energy minus 322.86 something, and for 5, 7, it is the energy is changing. So let's remove these unwanted lines, unwanted text. Just select this
सर कुछ
slash
समझ नहीं आ रहा है
sorry ये दुष्यंत
जी sir.
Did you get that folder, the T2 folder?
Yes sir.
In that folder, you have these four more folder: cutoff, kpoint, lattice optimization, and final optimization optim. Right?
Yes sir.
In each folder, you have a script named energy cutoff script, something script cutoff.sh. Right? Dushyant, Dushyant, are you there? Dushyant, are you there?
अभी उठा है, सो लिया 2 घंटे.
What you have to do, I am repeating it again. You have to optimize the K points, cutoff energy. First thing is cutoff energy. Optimize the cutoff energy and take that value. Then go to the K points. Optimize that K points using the script. So when you run this script, you have multiple files, multiple folder you have to grab the total energy from each folder. So how you will be grab? Using this command grab total equal to */star dot out, and save this total energy in energy.dat file. And your next step is to open that file gedit energy.dat. Let me open it again. Your file is something like this. Then you have to remove these unwanted text because we want to plot in it in X and Y column. So we will press Ctrl H and replace it with nothing and save it. Then cross it. Now plot it in XM grace energy.dat. Energy.dat, and you can see here, as you increase your K points, your energy is going toward optimum condition. So here you can see the optimized or the minimum energy is here. I think it is around 771. So our K point will be 771.
Narendra, there was another script in this folder, na? Gate script along with that.
Yes, sir. I removed it to show how we can grab the energy.
Yeah, okay. Because it's easy and this may save some time.
Yes.
Just to give the output file name and run that second script, then it will create that. Okay, this is a good exercise. But also now you can provide that.
Just to demonstrate how.
How it is working. Okay, good one.
Yes. Yes, sir.
So after this, this is just for the optimization. Yesterday we have optimized that exchange correlation function and one basis sets. And today we have to optimize the structure. So to optimize the structure, we have 4 steps. And in literature, also in the paper, we write these steps. So for optimization, we first optimize base cutoff, then kpoint, and then lattice constant, then the final optimization. So each and every steps are important, and you have to follow this. After going to this tutorial, your assignment is you have to watch lecture number 7 in my channel. So that detail is also there, and you can revise this particular exercise. Okay, proceed.
Okay. So you can see here your the minimum energy is around 771. So our K point in this script is now 771 because we get the minimum energy around 771. Just save it, cross it. Let me go to the next folder, or you can just copy this file, this script, but I pasted it into each folder. So let me, or you have already here, so I'm not going to paste it again. So you have this folder. Now my mesh cutoff, the optimized mesh cutoff that I optimized in step number 1 is 400 readable, and my K point is 771. The next step is to optimize this lattice constant. It was 1.0. Now I want to change this lattice constant. Lattice constant is related to your vectors, cell vectors. Suppose this is your vector, cell vector, and you have 2 atoms here, carbon and carbon. So we want to move this lattice constant, like it is 1 angstrom, 1.0 angstrom. It is a 1 angstrom. So what I want to do, I want change this value around this lattice constant to get the minimum energy around it. So what I will do, I will change this lattice constant from 0.95 and calculate the energy corresponding to it. Then move it to 0.96 and calculate the energy. The same like we did, and 1 point up to 1.5 and calculate the energy. Then I will plot energy versus lattice constant, and it will give me another minimum energy. So for that, I need to define my starting point of the lattice constant, that is 0.95, or you can go with 0.93 in this step of 0.01 up to, let's say, 1.15. Save it and make sure put dollar icon here. Dollar sign means the variable of this script. So this script will change the lattice constant first 0.93, then run the CS star, then 0.94, 95, 96, and so on up to 1.15. Just save it, proceed the same step to run this calculation. First one is chmod plus x and script underscore op.sh. Hit enter. If you hit ls, you can see your script is in the green color now. Now you have to hit / and script.opt.sh. Hit enter. It start running. It will take around 5 minutes. So let me revise again what we are trying to do. To optimize, to relax any system, we have to follow 3 steps. First one is the optimization of mass cutoff. First one is the optimization of mass cutoff energy. We will do it with script, and you have mass cutoff versus energy plot is something like this. It will give you the optimized or the mass cutoff that you need. In our case, we found it is around 400 readwork. Then the next step is the optimization of K points. In that case, the same we have graph K point versus energy. It will give you the minimum energy correspond to K points, different K points, like 1, 2, 3, 4. In our case, we found the minimum energy which correspond to 7. I think 7. Yes, 7. Here is 7. So we have two optimized value now. For mass cutoff, it is 400 readwork, and for K point, it is 7 cross 7 cross 1. Now we are in the third step, that is the lattice constant. Lattice constant. Here we will get the same graph like energy versus lattice constant, and we will have a minimum energy, maybe somewhere here. We will get this energy, then we will move to the final optimization. Okay, calculation is finished. Now we will grab the energy similar like before using the grep command, grep space total equal to star/star dot out, that is star/star dot out, and save it as a energy dot dat. Now you can see we have energy dot dat file. Let's open it with gedit. The same step we did in step number 1 and 2. Gedit energy.dat, hit enter. Now again we want to remove these lines. Just select it and press Ctrl H and replace it with nothing and save it. Pause it. Now we want to see the trend of our energy, how it is varying with the lattice constant, with varying the lattice constant. So X and grays, energy dot dat. Hit enter. You have a graph, something like that, something parabolic. That means, let me first double click it on this line. Select a symbol circle and press OK. Apply. If you want to zoom it, let me zoom it from this region, or let me explain it first. So what happened when the lattice constant 0.94, the energy is here. As the lattice constant is moving, the energy is also going toward minima, and at a particular value, particular lattice constant, we have a minimum energy, and after that if you increase the lattice constant, the energy is increasing again. So because we need to optimize to relax the system, that means the minimum energy where it has a minimum energy, we have to find that one. So in that case, in our case, we have the minimum energy is around, that is 1 or 1.1. Let me zoom in this area again. Let me zoom it. 1 or 1.1, both are the same. So I can take my lattice constant either 1 or 1.01. So here I'm going to take it 1. Cross it. We did 3 steps. Mass cutoff, we found 400 read work, the minimum energy around 400 read work. Then the k point 7 cross 7 cross 1, and the lattice constant is 1.0 angstrom.
Hello, Narendra sir.
Yes.
Sir, I have a query here. Like you said, lattice constant 1.00. No, I think to get the lattice constant, we have to multiply this number with the lattice vector. No.
Sorry.
To obtain the lattice constant, no, I think we have to multiply this number with the lattice vector. No, A and B.
Yeah. Yes.
Yeah. I think that should be the case.
Yes, but just to demonstrate, I increase I vary the lattice constant only. The lattice constant and lattice vector are just a multiple of each other.
Yes.
That lattice constant constant exercise, we did it in yesterday's hands-on session.
Yeah. Oh, okay, sir. I missed that one. I think.
Yes.
Thank you very much.
Okay. So now go to the 4th folder, the optimum one. Here our FDF file. Now here we have to put our lattice constant, optimize the lattice constant value that we get. That is 1 angstrom. Okay. Then the mass cutoff, the optimized mass cutoff, we have 400 read work, just 400 read work, and the k point It is 7771 and save it. Now we did these calculation. Step 1, 2, 3. The CG step 0, 0, 0. CG step was 0. But now we are doing the final optimization. We have to put our CG step 1000, the maximum CG step. So in the fourth step, we will put our CG step 1000, the maximum. You can save it. I already put 1000 here. Save it, cross it, open a terminal, and now run the siesta using siesta command. Siesta less than carbon.fdf file, then this symbol and TWE and log.out. It will take a few minutes. So up to now, anyone have any question you can ask, we can discuss. Sajal sir, you are doing good. So anyone have any question, or should I move forward?
Hello, sir. I have one
Yes.
question, sir.
Yes, sir.
Sir, in the lattice parameter optimization script, we have written the lattice parameter using $sign. But in the other
Yes.
cases, in the FDF file, there is no option for that.
No, we put the $sign. Here you are asking this the first one. Let's say the cutoff energy.
Yes,
if you
sir.
see here, we put this $sign. You're talking about this, or
No, sir. No, sir. There is no lattice parameter, sir. In this case.
no? We have the initial one. It was 1. Just one.
Okay,
The
sir. Okay, sir. Okay, sir.
default
Thank you,
value.
sir. Thank you, sir.
Yes.
I think you are talking about that lattice vectors are there in place of lattice parameter. So that the size of this simulation box, it is defined in two terms. Either it's given in terms of lattice parameter where alpha, beta, gamma, and ABC, that these are given as per that crystallographic terms are there. So in solid state physics, when we define that box, means inside that the atoms are there. So that is in terms of ABC, the size along x-axis, y-axis, and z-axis, and the angles between two axes, that is alpha, beta, gamma. So these lattice parameters are those parameters. And second, in some FDF file, in test files are there, in place of this lattice parameters, lattice vectors are there. Even in that output file that mentioned by Narendra, that in output file also, in place of this lattice parameter, you will have lattice vectors. So don't confuse with both are same, but the way of writing is different. So in this lattice constant variation, you can use this, or also that a lattice vector term also.
Thank you, sir.
Shweta is asking what should I do when showing error that atom are too close in the script file. In that case, you need to check the coordinates of your FDF file and the lattice parameter as well. Sometimes there is overlapping of your coordinates, so you need to cross check it.
Sir, kindly explain the energy cutoff convergence point again, sir.
Energy cutoff with lattice constant?
No, sir. Mesh cutoff energy.
Mesh cutoff, and you know, in morning set, not today, but yesterday's Professor Rodrigo explained that one algorithm how DFT will work. He showed one algorithm that is something solving the Cohen-Sham equation. Then we are calculating the density of the system and something like that. If you remember.
No, sir. Actually, I am not talking about that. The energy value we should choose for the optimization.
Yes.
Okay, sir. From the graph,
Yes.
we have found out
Yes.
which value we should take from the graph. So just started the minimum from the starting point or the from the end point, sir.
So no, after a particular point, it is becoming stable. I mean, there is just minor change in the term of it. Maybe in change is just 0.00023. So if you check the energy, you can
Okay,
see here. If you see this energy.at file, you can see your energy is changing. But after you can see 350, it is not changing as much. Here you can see 625, 5 last 3 digit, 561, 471. But after 350, it is 937, 926, 945. Now the energy is changing only in these two places. So you can take this value, your mesh cutoff, because
okay, sir.
energy.
Thank you very much.
Yes, energy is just less changing after a 350 read work. Okay, now the calculation is finished. Again, we have to do the same step that we did day one hands-on session. Just open your out file, gedit log.out, and search for relaxed atomic coordinate, Control F, and search for relaxed, RELAX, relaxed. You can see you have relaxed atomic coordinate here. Just copy this coordinate and paste it in your FDF file and save it. Now your system is fully relaxed. So, sir, how much time I have?
We have 12 more minutes only.
12 minutes.
Yeah.
Should I
Can
move for
complete
band
DOS.
DOS?
We can. So tomorrow we have to perform that bands plot and PDOS.
Okay. Just
Actually, that
save it.
optimization process, it takes time to understand as well as perform. If that system is properly optimized, then that analysis of properties or other plotting, use of other plotting tools are easy. So you have to do some practice and for different materials, and then you can learn this. Actually, Pandey sir gave such a statement that you have to feel the materials. Means whatever you are trying to do with your computer, with your and your material, you have to feel that material, what is happening there. when you are running that program. So in that maze cutoff, what is that? That kpoint, what is that? You have to Google it. Yes, yesterday I told that you have to make that Google as a good friend. So क्या होता है ये सारी चीजें ये आपको डिटेल्स देखना चाहिए और ये ऑप्टिमाइजेशन का प्रोसेस है बिकॉज वी हैव टू बैलेंस two things, one accuracy as well as computational time. Sometimes that maze cutoff is too high. So if that maze cutoff is too high, obviously that will consume more computational time. That's why also the same thing is for k points. If k point is much more, then obviously that computational time will be high. So many people just use some default k points and maze cutoffs and give the result, and that is not good. We generally follow that accuracy. That's why we optimize the system using this. Otherwise, many papers you can get that maze cutoff is about 200 to 250 k point. That is about 5 to 7. And latest variation, I think they have performed, and that latest variation and that final optimization with some CG points they can do. So, but we have to optimize the system by using this optimization process of these parameters. Okay, proceed, Naren.
Yes. Now we will plot the density of states. For that, we need a utility called EIG2DOS. When you run this final calculation inside this optim folder, you have this EIG file. Now we need a utility. If you open this file, you can see the format is something like this. Now we need a utility that can change the format in X and Y. For this utility, EI2DOS, you have to go inside your Siesta directory that you installed or Siesta folder that you installed. We installed V5 4.15 version. So I'm going to here. Then you have to go util. Then you have to find EIG2DOS. Here you can see EIG2DOS. Everyone get this folder EI2DOS. Just open it. In your case, you have to open the terminal here. You have to open the terminal here and type make. M-A-K-E, make. Then press ls. Now you can see you have one binary file in green color. Type make, go to your Siesta, util, then EIG2DOS, open terminal here and type make. It will create a EIG2DOS file for you. Now copy this file to user local bin, therefore you can access it easily. How you will be copy sudo cp, then file name EIG2DOS is /user usr /local/bin. I'm writing in this command in chat box sudo cp EIG2DOS space usr space local space bin and press enter. It asks for password. Enter your password. Done. Now cross it. go to your folder. Back to that folder, Day-2, and this optim folder. Now open a terminal here. Jitendra, it is not Jitendra, who is this? Jharneshwar. It is problem with your virtual box. You have to reinstall it or make sure the virtualization is on in your BIOS system in your laptop. So now we copied that EIG2 file in our bin. Now we will use this EIG file, EIG2 DOS space -s. -s means the sharpness of the peak. 0. I'm using 0.02 space -f. -f means shift the Fermi energy. Then -n, number of points between your values that we are going to give. Let's say 1000 minus capital N. Let's say from -5. Let me refresh my memory. It is capital N or M? It is, I think, M, N. Let me refresh my memory, then I will explain. -N, capital M, 5, start dot. Yes. So the command is EIG2 DOS, the utility we copied, then -f. S is the sharpness of the peak. I'm using 0.02 -f to shift the Fermi energy. -n is 1000. That is the point between my minima and maxima. My minima is -5 and maxima is 5. In between these points, I am going to take 1000 number of points. -m is for minima. I am starting with from -5, and capital M is for maxima up to 5. Then your file name, I'm using here star.eig, and greater than DOS.dat. Hit enter and type ls. Now you can see a DOS.dat file is here. Now plot it using XMGrace. XMGrace DOS.dat. This is my DOS, but the one thing that I took very sharp peak. Let me change it. Sharpness. Let me take it 0.2 and enter. Plot the file using XMGrace. You can see cross check it. I'm feeling there is problem with this DOS. Let me cross check it. I'm using another utility. I think the DOS should be is not correct, but I will cross check it, and we will discuss it tomorrow. But the thing is, the method is this to plot the DOS. Tomorrow we will follow one more another method to plot the DOS. I think I need to shift the energy. So this F command will work for shift the energy. Sir, this F command is will work for shift the energy. I'm feeling that this F is not working. Verma sir.
Yes.
We are not.
This F command will work in EIG to DOS.
Just to use that minus F just in the front, EIG to DOS. So first copy that EIG to DOS and minus F, use that minus F first.
Is it in capital or small?
Here, minus, no, small. And S02, yes, N is equal to this. Okay, now plot it.
But
Is
for
it?
graphene, it is working, but the thing is for graphene, we have this gap. How this possible?
There may be some error actually. For graphene, it must be about 0. So
yes,
maybe during optimization there may be some problem, because I have checked this several times.
yes. Or tomorrow we will cross check it with the FMP DOS.
Even yes, with PDOS and that band plots, you have to check this.
Yes. So tomorrow we will do the band and DOS as well, because I don't think so. This one is the correct one. For today, you have assignment to optimize your silicon bulk system. This is for 2D graphene sheet. Bulk is 3D. When you do the optimization, kpoint optimization, make sure your kpoint should be in X, Y, and G direction. But today, you have to do the optimization of silicon. Go to exercise number 2. You have silicon FDF file. Copy the script from here and run it and optimize it. So anyone have any question up to this regarding the optimization?
Now session is open for discussion. If anyone has any question, then you can answer.
So all these lectures are in live mode in your college website, YouTube channel.
Yes, sir.
So you should follow that one. And repeat that this exercise if you have laptop or desktop at your home. And also you can follow, you can watch these lectures in my channel for DAS, PDAS, and
excuse me, sir.
Hmm.
Sajal sir is sharing one screenshot in the group. Sir, in your screenshot, I can see you put -M space E.
Oh, sorry, sir. Sorry, sir.
Yes.
It should be +5, sir.
Yes.
Okay, thank you.
Thank you.
Okay, then I would like to thank Professor Mohan L. Verma sir and Narendra Kumar sir for your helpful hand-on session. Now we are going to end today's session. Thank you all.
Thank you, ma'am.